In this video, we're going to talk about solids, liquids, and gases. In particular, we are going to focus on how to represent them using particulate-level models. We'll look at a lot of pictures, and we'll also look at several PhET simulations because they do a very good job at this. Let's start with solids. The molecules that make up solids are generally close packed together, and they aren't free to move about like the molecules in liquids and gases are. In solids, we generally see just vibrational motion. We don't see rotation of the molecules, nor do we see translation of the molecules. You remember from geometry, rotation is spinning, translation is moving from one place to another. Solids are rigid. They don't take the shape of their container. They do not expand to fill the entire available volume like a gas does. They keep their shape. Solids are non-compressible, which means you cannot compress or squish them easily because there's very little space between the particles. Solids are divided into two categories based on how their particles are arranged. In crystalline solids, the particles in the solid are arranged in regular patterns or lattices. Examples include salt, minerals, and metals. You may have noticed that some of these are ionic compounds and some of them are metallic. Covalent compounds can also be crystalline. You typically can't compress these. They have a definite melting point since the bonds or forces between the particles have equal strength. When you apply heat, the forces or bonds all break at the same time. Crystalline solids also tend to have cleavage. When you break them apart, the pieces have straight edges or planed surfaces. Metals are a bit of an exception since their sea of electrons structure tends to make them malleable and ductile instead. Amorphous solids are solids in which the molecules are arranged less regularly. They don't have a repeating lattice pattern. Many of these are made of molecules that just don't stack up well. Examples of amorphous solids are glass and rubber and plastics. Amorphous solids do not have a definite melting point, but they tend to melt gradually over a range of temperatures. They melt into a softer state before they turn into a liquid. Amorphous solids don't have a regular plane of cleavage when you cut them. They tend to break into random curved lines. Many amorphous solids are polymers, long chains of repeating subunits that are linked together. Examples of these include polystyrene, PVC, and others. Although some of these polymers can line up to form a more crystal-like structure, others are just a tangled mess. Now let's talk about liquids. The particles in liquids are in close contact with each other, and they're continually moving and colliding. The arrangement and the movement of the particles are influenced by the nature and strength of the intermolecular forces that are working on them. For example, whether they're polar or whether they have hydrogen bonding. Temperature also plays a role in the movement, because the higher the temperature, the faster the particles move. The solid and liquid phases for a particular substance typically have similar molar volume because in both phases, the particles are in close contact at all times. Just like solids, liquids are non-compressible, at least not under normal circumstances. In the gas phase, the particles are in constant motion. Their frequencies of collisions and the average spacing between them are dependent on temperature, pressure, and volume. Because of this constant motion and minimal effects of forces between particles, gas has neither a definite volume nor a definite shape. Gas particles are far apart, and there's lots of space between them. Hence, gases tend to be compressible. In particle diagrams like this one, it's common to see arrows attached to the particles. The arrows denote the speed or energy of the particle. The longer the arrow is, the more kinetic energy there is, and the faster the particle is moving. Remember, temperature is a measure of average kinetic energy, and some particles are moving faster, and some particles are moving slower in any given sample. In summary, you should now be able to describe and explain the different properties of solids, liquids, and gases, and you should be able to explain what is happening on the molecular level and represent this using particle diagrams.